What specific problem does the UKT model aim to solve in the context of knowledge tracing, and how does it address the limitations of existing methods?
The UKT model aims to solve the problem of accurately assessing students' knowledge mastery in knowledge tracing (KT) by effectively modeling uncertainties in student interactions, specifically addressing both epistemic and aleatory uncertainties. Existing methods often overlook these uncertainties, leading to biased assessments that do not reflect a student's true knowledge level. UKT introduces a stochastic approach that represents each student's interaction history as a Gaussian distribution, where the mean indicates the student's baseline knowledge and the covariance captures the uncertainties involved. Additionally, it employs a Wasserstein distance-based self-attention mechanism to monitor global changes in knowledge states, rather than relying on point comparisons. To enhance robustness against aleatory uncertainty, UKT incorporates an aleatory uncertainty-aware contrastive learning mechanism that constructs negative samples reflecting careless errors and lucky guesses, thereby improving the model's accuracy in predicting knowledge mastery.
How does the proposed UKT model work? Illustrate the method step by step, detailing the roles of the stochastic embedding layer, Wasserstein attention, and contrastive learning.
The proposed uncertainty-aware knowledge tracing UKT model operates through a series of structured steps to effectively capture and manage uncertainties in student interactions. First, it utilizes a stochastic embedding layer that represents each student's interaction history as a Gaussian distribution, where the mean indicates the student's baseline knowledge and the covariance captures both epistemic and aleatory uncertainties. Next, the model employs a Wasserstein-based self-attention mechanism to analyze these Gaussian distributions, allowing it to track changes in knowledge states by measuring the discrepancies between distributions rather than individual points. Finally, to enhance robustness against aleatory uncertainty, UKT incorporates an aleatory uncertainty-aware contrastive learning layer, which constructs negative samples that reflect careless behaviors and lucky guesses, thereby maximizing mutual information between perturbed views. This multifaceted approach enables UKT to accurately assess students' knowledge mastery while mitigating the impact of random errors in their responses.
Can you provide a simple yet illustrative example of how the UKT model processes a student's interaction data and how it distinguishes between epistemic and aleatory uncertainty?
The UKT model processes a student's interaction data by representing each interaction as a Gaussian distribution characterized by a mean and covariance. For example, if a student answers a series of math questions, the mean reflects their baseline knowledge level, while the covariance captures the uncertainties in their learning process. Epistemic uncertainty arises from the student's varying understanding of concepts, which can be quantified through the covariance embedding, indicating their cognitive differences. In contrast, aleatory uncertainty is represented by random factors such as careless mistakes or lucky guesses. For instance, if a student guesses the answer to a question correctly, this would be captured as aleatory uncertainty. The UKT model employs an aleatory uncertainty-aware contrastive learning mechanism to construct negative samples that help the model differentiate between these two types of uncertainty, thereby enhancing its robustness against misleading data while retaining valuable insights from epistemic uncertainty.
What are the theoretical and practical benefits of using the UKT model compared to traditional knowledge tracing models like DKT or AKT?
The UKT model offers significant theoretical benefits over traditional knowledge tracing models like DKT and AKT by explicitly incorporating both epistemic and aleatory uncertainties into its framework. Theoretically, UKT models student interactions as Gaussian distributions, allowing for a nuanced representation of knowledge mastery that captures the inherent uncertainties in learning processes, which traditional models often overlook. Practically, UKT enhances prediction robustness by employing an aleatory uncertainty-aware contrastive learning mechanism, which mitigates the impact of random errors and guesses, leading to more accurate assessments of student knowledge. Experimental results demonstrate that UKT consistently outperforms DKT and AKT across various datasets, particularly in terms of AUC and accuracy, validating its effectiveness in real-world applications. Overall, UKT's ability to model uncertainties provides a more personalized and reliable approach to knowledge tracing, addressing the limitations of deterministic methods.
How was the UKT model validated or tested, including the specific datasets used and the metrics for performance evaluation?
The UKT model was validated through extensive experiments on 6 benchmark datasets: Assessments 2009, Algebra 2005, Bridge 2006, NIPS 34, Assessments 2015, and POJ, which collectively encompass millions of student interactions and various knowledge components. The performance evaluation metrics used were area under the curve, AUC, and accuracy, allowing for a comprehensive assessment of the model's predictive capabilities. The experiments involved a standard 5-fold cross-validation approach, reserving 20% of the student sequences for evaluation while training on the remaining 80%. Results indicated that UKT consistently outperformed existing baselines across all datasets, particularly in AUC scores, demonstrating its effectiveness in capturing and predicting student learning behaviors. Additionally, the model's robustness against aleatory uncertainty was highlighted through comparative analysis with other models, confirming its superior handling of uncertain environments.
What limitations or drawbacks does the UKT model have, and what future work do the authors suggest to improve or extend this research?
The UKT model, while innovative, has limitations primarily related to its handling of aleatory uncertainty. The authors note that excessive emphasis on aleatory uncertainty during training can lead to a decline in model performance, as it may divert focus from accurately predicting student knowledge levels. Additionally, the model's reliance on Gaussian distributions to represent student interactions may not fully capture the complexities of all learning behaviors. For future work, the authors suggest exploring alternative methods to better model aleatory uncertainty and enhancing the robustness of the model against various types of uncertainties. They also imply that further research could investigate the integration of additional contextual factors that influence student learning, potentially leading to more personalized and effective educational assessments.